Assalamualaikum. Welcome to UEE 316 project presentation. I'm Farhan Alvi, 1706-183 from Group 2. My partners are Farhan, Hamid, Fedul Hassan Fahim, Taki Tajor Ali, and Sharer Kobi. Our project is about battery charger with variable DC output using a buck boost converter with auto cutoff feature. We wanted to do the hardware implementation of our project, but due to the current COVID situation, we were instructed to perform software simulation in Simulink. Our project highlights the following incidents: a 12-volt battery management and auto cutoff mechanism and DC to DC converter implementation. Thank you.
The entire circuit implementation at a glance through breakup discussed in the upcoming slides and video. This is the following approach which were taken to perform the simulation. A bidirectional DC-DC buck boost converter was designed to implement a battery management system. An idle switching was implemented with respect to the voltage capacity of the battery. Reference current value was taken to initiate either charging or discharging of battery. A PI controller was introduced to reduce the steady-state error of the feedback along with gaining overall stability of the current.
Bidirectional DC to DC converter. As the left side of the circuit is 24 volt and the right side is 12 volt side. So the converter works in buck mode when the current flows from the high voltage side to the low voltage side. In other words, when the battery is charging. Conversely, the converter works in boost mode when the battery is discharging. Now I'm explaining the charging discharging states. At charging state, when the MOSFET 1 is on and the MOSFET 2 is off, the battery is charging directly from the input or the source. And also the inductor gets charged. After that, when the MOSFET 2 is on and the MOSFET 1 is off, the battery continues to get charged via the inductor. At discharging state, when the MOSFET 1 is on and the MOSFET 2 is off, the battery discharges and gives power to the 24 volt input source. In a way, battery acts as a source now, then MOSFET 2 is on and MOSFET 1 is off. The battery continues to discharge via internal impedances.
Hello, this is 1706180. I am going to describe whether the battery is in charging or discharging mode by the help of a reference time. Here, positive reference value of current will operate the circuit in buck operation and charge the battery, and the negative reference value of current will operate the circuit in boost operation and discharge the battery, illustrated in the next figure. Here, when the reference current is negative, we can see that IVAT current will be reversed and the converter acts as a boost converter, and this is the discharging mode of the battery. Likewise, the charging mode for positive reference current. Here, we used a negative feedback system to calculate the steady state error, for which we used a PI controller to stable the system and minimize the steady state error. And then the limiter here help us the current to be flow before the between the reference range. Thank you.
Assalamualaikum. This is 1706-175 Farhan Hamid. On behalf of Group 2, I'm here to demonstrate our EEE 316 project demonstration. As previously told, all of our approaches have been successfully implemented in this MATLAB Simulink file. Here we can see that we have used a reference current value, which indicates the circuit acts in a discharging manner for any negative value set here. And also vice versa, for any positive value set here, the circuit acts in a charging manner. We will see a demonstration of it, like for the -1 value, and we see that the battery is currently at 11.93 nominal voltage. So for the -1 reference voltage, if we run the circuit for 0.2 seconds, we will see the battery gets discharged and the voltage of it starts decreasing. Here, the battery is discharging and acts as a source, and thus it feeds the rest of the circuit its power. And if we want to see the corresponding charging state of our circuit, we will see that for any positive value we give, the battery will act as a load. So here, when we put 1 as a positive value, the battery starts charging itself from 11.93 volt to a voltage greater than it for the given 0.2 seconds. Afterwards, we will see that the entire circuits will produce a lot of hefty instability along with a lot of steady state errors. So we have compensated the entire system with a PI compensator, which gave us system stability along with very low steady state error. And afterwards, we give this output to a current control DC to DC PWM generator, which gives us 2 ideal PWMs, which are used to power up the MOSFETs here. For the battery, in our case, and its auto cutoff version, we have implemented an ideal switch with it. The ideal switch acts in the manner that it charges the battery for a certain period of time and then gets open circuited, and afterwards the battery discharge nominal current has a nominal voltage drop in it, and thus the battery comes around to its ideal value of 12 volt. For this, we will now see the project simulation, and for the entire part, will see for the 0.75 seconds, we have given a state generator signal for which the total 0.75 seconds have been divided into two parts. For the first 0.5 seconds, the battery will get itself charged, and for the later 0.25 seconds, the battery will have its internal discharge current having a nominal voltage drop in it to result in the final 12 volt after the stoppage time. So if we run the circuit here right now, we will see for T increasing, the battery voltage is increasing. Here, both of the MOSFETs are now operating one after another in an inversely manner, and afterwards, it is also getting compensated in each of these steps with a positive value here, and thus the entire circuit is charging heftily. And after the T crosses the 0.5 mark, the circuit gets open, and thus a very nominal current flows into the battery, and so the discharging current of the battery itself has a voltage drop, which makes the BUET gets again lowered down to 12 volt for our given optimum time. So this is all together the process of how this bidirectional DC to DC converter works in support of batteries charging and discharging with an ideal auto cutoff scenario. Thank you. In our second demonstration, we have implemented a relay connection connected to the battery bus voltage. Here, the relay has a 12 volt switch on point, which will keep the output at 12 volt, making it an automated cutoff at 12 volt, and any point below that will keep the voltage at 11.90 volt. So while charging the battery, when it reaches the upper limit of 12, it will automatically get cut off and show the 12 volt. So if we set the battery nominal voltage in between the upper and lower values, say 11.93 volt, and start the simulation for charging the circuit, then we will at first see 11.9 volt at the lower limit, and as the battery progresses to charge, we will eventually see the upper limit of 12 volt, and then the battery will get itself cut off, and it will then hence prove the automated cutoff point. So here in our screen, we can see that at this time, the battery has automatically cut off at 12 volt, thus implementing the automated cutoff feature of this project.